Hey everyone, welcome to this deep dive into regularization techniques in machine learning, the secret sauce that keeps our models from overfitting like a kid memorizing an entire textbook instead of actually learning. If you've ever trained a model that performs amazing on training data but crashes and burns on new data, yeah, you've met the overfitting monster. But don't worry, today we're going to tame that beast with regularization. Before we jump in, hit that subscribe button and follow me on LinkedIn. Let's build this AI community together. Now let's roll. Hey, let me ask you something. Have you ever trained a machine learning model and felt like an absolute genius because it hit 98% accuracy on your training data? You're thinking, damn, I just built the next GPT-4 AI, and then boom, you test it on real world data and it fails miserably. Your high-performing model turns into a hot mess, like a student who memorized the entire textbook but can't answer a single real-world question. Yeah, that's called overfitting, and trust me, it happens to the best of us. But don't worry, today I'm going to give you the ultimate weapon to fight back. It's called regularization, and it's the secret sauce that separates a good model from a great one. So what is it? Let's break it down in simple terms. Imagine you're baking a cake. Yeah, we're going full master chef on this one. You've got the flour, the eggs, the butter, and of course the sugar. Now, sugar is amazing. It makes your cake sweet and delicious. But what happens if you dump in an entire bag? You don't get a better cake. You get a sickeningly sweet disaster that nobody wants to eat. Regularization works the same way. A machine learning model without regularization is like that sugar overdose. It tries to learn every single detail, even the ones that don't matter. It memorizes your training data instead of actually learning patterns. And the result, it fails when faced with new data. Here's the deal. In machine learning, we always want a model that generalizes well, meaning it shouldn't just perform well on data it's seen before, it should handle new unseen data like a pro. And regularization helps us achieve that by gently forcing the model to keep things simple. Think of it like training for a marathon. If you only train at one exact speed on one exact track, you're going to be screwed when race day comes and you face hills, wind, and all kinds of real-world conditions. Regularization is like a personal trainer that forces your model to be flexible, adapt, and perform well no matter what data set it encounters. Now, how does it actually work? Without getting too technical just yet, here's the big idea. Regularization adds a penalty to how complex our model can be. If our model tries to use too many parameters or give too much importance to small details, regularization steps in and says, hey, calm down, focus on the bigger picture. It literally shrinks unnecessary parts of the model so it can generalize better. And the best part? Regularization isn't some complicated magic spell. You can apply it with just a few lines of code. But before we get there, you need to understand why it's so important and how to pick the right type of regularization for your model. Because trust me, using it wrong is just as bad as not using it at all. Now that we've set the stage, let's move on to the next part. Why overfitting is a nightmare and how regularization saves the day. Okay, picture this. You're in college and you have this one friend. Let's call him Tom. Now, Tom is a total nerd, but not in the cool, I build robots in my garage way. No, Tom is the kind of guy who memorizes entire textbooks word for word. Like literally, if you ask him, what's on page 143 of our physics book? Boom, he can recite it verbatim. You'd think he's a genius, right? Well, until exam day comes. The professor doesn't just copy-paste questions from the book. Instead, they throw in some real-world problems, things that require actual understanding, not memorization. And guess what? Tom chokes. He panics because he never actually learned the concepts, he just memorized words. Meanwhile, your other friend, Sarah, the one who actually understood the material, she crushes the test. And that, my friends, is exactly what happens when your machine learning model overfits. A model that overfits is basically Tom. It memorizes every tiny detail from the training data instead of learning the actual patterns. It performs amazingly well on data it has already seen. But when you give it something new, game over. Just like Tom on that test. So, why does this happen? Well, there are a few main reasons. First, if your model is too complex, meaning it has too many parameters, too many layers, too many degrees of freedom, it has the power to fit everything, including random noise in your dataset. It's like drawing a crazy squiggly line through every single data point instead of recognizing the actual trend. Second, if you're working with a small dataset, your model might force itself to find patterns where none exist. It's like trying to predict the stock market based on just 1 week of data. You're going to come up with a bunch of nonsense correlations that don't actually hold up in the real world. And finally, noise. If your dataset has errors, outliers, or irrelevant details, an overfitted model will obsess over those tiny quirks instead of focusing on the real trends. Now, here's where it gets scary. Overfitting isn't just a small problem. It can literally make or break your model. Imagine you're building a fraud detection system for a bank. During training, it memorizes all the past fraud cases perfectly. But the moment a new type of fraud happens, it misses it completely. Boom, millions of dollars lost. Or let's say you're working on a medical AI that diagnoses diseases, it memorizes your training set, but the moment it sees a new patient, it misdiagnoses them because the case doesn't match anything it's seen before. In the real world, that's not just a bad model, that's dangerous. But here's the good news. Overfitting has a fix. And that fix is what we're about to dive into next. Regularization, the secret tool that forces your model to learn smarter, not harder. Trust me, you don't want to miss this next part. Okay, so we've established that overfitting is like that one guy who memorizes every single word in a textbook, but completely fails when faced with real-world questions. Now, here's the million-dollar question. How do we stop our models from turning into that guy? The answer? Regularization. And not just any regularization. There are different types, each with its own strengths and weaknesses. Think of it like tools in a toolbox. You wouldn't use a hammer to fix a computer, right? Just like you wouldn't use the wrong type of regularization for a given model. So let's break it down into the two big ones, L1 and L2 regularization. Let's start with L1 regularization, also known as Lasso, least absolute shrinkage and selection operator, but let's be real, nobody calls it that. L1 regularization is like a ruthless minimalist. Imagine you have a cluttered apartment filled with stuff you don't actually need. L1 walks in, takes a look around, and says, "Nope, we're getting rid of half this junk." That's exactly what L1 does to your model. It literally eliminates unnecessary features by shrinking their coefficients to zero, meaning if a feature isn't useful, L1 just deletes it. Gone. Poof. No more wasted space. This makes L1 regularization perfect for feature selection, especially when you're dealing with huge datasets with a ton of variables. Think genetics research, where you have thousands of genes, but only a few really matter, or high-dimensional finance models where some features are just noise. L1 forces the model to focus on what's actually important. But then we have L2 regularization, also called ridge regression. And L2, it's more like a strict coach. Instead of deleting features like L1, L2 says, "I'm not letting you go crazy with any one feature. You're going to keep it balanced, controlled, and disciplined." L2 shrinks all feature weights gradually. It reduces their impact without eliminating them completely. It's like saying, yeah, we're keeping all your data, but we're going to make sure nothing gets too much influence. This makes L2 perfect for models with correlated features, where you don't want to delete anything, but you need to control complexity. It's widely used in image processing, speech recognition, and deep learning models, where every input has some importance, but you don't want any single feature dominating the prediction. But wait, What if you want the best of both worlds? Enter elastic net regularization. This bad boy is a mix of L1 and L2. It removes some features, L1 style, but also smoothly shrinks the others, L2 style. It's like the Goldilocks solution, not too aggressive, not too soft, just right. Elastic net is super useful when you have lots of correlated features and need both feature selection and regularization. Think of it as a well-balanced meal. You're not cutting out all the nutrients, but you're also not stuffing yourself with junk. So, quick recap before we move on. L1, Lasso. Minimalist deletes useless features. L2, Ridge. Disciplined coach keeps everything but balances it. Elastic net, hybrid, a mix of both. But now comes the real question. How do these actually change a model's behavior? What's happening under the hood when we apply them? That's what we're diving into next. Get ready for some math, but don't worry. I promise it won't hurt. Now let's turn up the intensity because here is where we really start to see L1 regularization, Lasso, in action. And trust me, if you're not already using Lasso, you're about to see why it's one of the most powerful tools in machine learning. Let me ask you something. Have you ever worked on a data set that had a ridiculous number of features? I'm talking hundreds, maybe thousands of variables. It's like trying to find the one good tweet in a sea of absolute nonsense. You know there's some valuable information in there, but you're drowning in noise. This is exactly where L1 regularization, aka Lasso, comes in like an overpowered cleanup crew. Imagine you're running a startup. You've got way too many employees. Half of them are just standing around drinking coffee and scrolling TikTok. You need to cut costs, but you don't want to fire the wrong people. What do? You bring in L1 regularization. L1 walks in, ruthlessly evaluates every employee, and fires anyone who isn't pulling their weight. Gone. Poof. Just like that, your company is leaner, more efficient, and performing way better. That's exactly what Lasso does to your model. It identifies which features are actually important and sets the rest of them to zero. No hesitation, no nonsense. Just pure, brutal feature selection. Let's take a real-world example. Say you're working with genomic data. You've got thousands of genes, but only a handful of them actually determine whether a person is at risk for a disease. If you run your model without regularization, it's going to overcomplicate things, trying to make sense of every single gene, even though most of them don't matter. But with L1 regularization, boom, the useless genes get knocked out, and your model hones in on the handful that actually predict the disease. It's faster, smarter, and way easier to interpret. And here's where it gets even crazier. L1 regularization doesn't just help with performance, it helps with explainability. Because it's literally removing useless features, it makes it way easier to understand what's actually driving predictions. This is huge in fields like medicine, finance, and law, where black box models are a huge problem. Now you might be wondering, this sounds great. Why wouldn't I just use L1 all the time? Well, here's the catch. L1 is brutal more than Mortal Kombat. Sometimes it deletes too much. If your features are highly correlated, it might wipe out some valuable information, leaving your model too simplistic. And that's where L2 regularization comes in, because unlike L1, L2 doesn't delete, it balances. And that's exactly what we're about to cover next, how L2 regularization, Ridge, takes a different approach to keeping models under control. Trust me, this is where things start getting really interesting. Hey, cowboy, we just saw how L1 regularization, Lasso, is like a ruthless manager, firing useless features and keeping only the essentials. But what if I told you that sometimes deleting isn't the best solution? What if instead of firing people, you could train them to be more efficient? What if instead of eliminating features, you could smooth them out, keep them under control, and create a balanced model? That's exactly what L2 regularization, Ridge, does. And trust me, this is a game changer. So let's imagine you're running a basketball team. You've got a few superstar players who take all the shots. They're flashy, they dominate the game, but here's the problem. They're also high risk. When they're hot, they carry the team, but when they're off, your entire team falls apart because nobody else knows how to step up. This is what happens in machine learning when some features become too dominant. They overpower everything else, and your model relies too much on them, making it unstable. That's where L2 Regularization, Ridge, steps in like a legendary coach. Instead of benching the superstars, Ridge tells them, listen, you're great, but we need teamwork. We're gonna spread the responsibility, balance things out, and make sure no single player dominates too much. And that's exactly what L2 does. It shrinks the feature weights, but never completely removes them. Instead of setting some coefficients to 0, like L1 does, it keeps everything but forces balance. So why is this useful? Well, think about a situation where all your features are important, but some of them are just too overpowering, like predicting house prices, where factors like location, square footage, and number of bedrooms all play a role. Without regularization, your model might decide that one of these factors is way more important than the rest, making the model unstable and sensitive to small changes in data. But with L2 regularization, your model learns to give weight to all important factors without letting one feature completely dominate the predictions. It's like teaching your basketball team to play together instead of relying on one superstar. Now, here's where L2 is different from L1. Lasso is a savage. It says, useless features, gone, don't need you. It's perfect when you have a ton of features, but many of them are irrelevant. L2 Ridge is a coach. It says, everyone contributes, but let's balance things out. It's great when all features are useful, but some are just too powerful. And here's the thing, neither is always the right answer. Sometimes you need to remove features completely L1, and sometimes you just need to keep things in check L2. But what if you need both? What if you have some useless features that should be eliminated, but you also have important features that need to be balanced? That's where elastic net comes in, the perfect hybrid between L1 and L2. And trust me, you don't want to miss this next part. All right, now we're getting to the real powerhouse of regularization, elastic net. This is where things get interesting because elastic net is like the best of both worlds. So far, we've seen two very different approaches. L1 regularization, Lasso, the ruthless minimalist that deletes unnecessary features by setting their weights to 0, L2. Regularization, Ridge, the strict coach that keeps everything but forces balance so that no single feature dominates. But what if I told you that sometimes neither is enough? Let's say you're running a company. You've got too many employees and some of them are clearly not contributing. At the same time, you've got a few key players who are doing too much and dominating the workflow. If you go full L1 Lasso, you fire too many people, sometimes even the ones who were actually useful. If you go full L2 Ridge, you keep everyone, even those who aren't pulling their weight. What you really need is a smart hybrid strategy. You need to fire the employees who add no value while also balancing the workload among the ones who stay, and that's exactly what ElasticNet does. It removes useless features, L1, while also keeping the important ones in check, L2. It's like a CEO with the perfect strategy, cutting waste but keeping the company balanced and efficient. So how does it work? ElasticNet takes both penalties, L1 and L2, and combines them into one powerful formula. Imagine you're a chef creating the perfect dish. L1 is like spice. It adds intensity but can easily overpower everything. L2 is like cream. It smooths things out but can make the dish too bland. ElasticNet blends them together in just the right amounts, creating a balanced, refined dish that works in any situation. Now, why is this useful in real-world machine learning? Let's take medical research. Imagine you're predicting which genes contribute to a disease. You have thousands of potential genetic markers in your dataset. L1 alone would eliminate a lot of genes, which might be risky because some genes interact with each other in subtle ways. L2 alone would keep all the genes, even the ones that barely matter, making the model more complex than it needs to be. Elastic net, it finds the best of both. It removes the genes that don't contribute at all while carefully adjusting the importance of the ones that do. And this doesn't just apply to genetics. ElasticNet is a game changer in areas like finance, filtering out useless indicators while keeping a balanced view of market trends. Natural language processing, selecting the most relevant words without overfitting to noise. Marketing analytics, keeping only the customer behaviors that truly impact sales while balancing them properly. So, quick recap before we move on. L1 Lasso removes features completely. Great for reducing dimensionality, but can be too aggressive. L2 Ridge keeps everything but balances them. Great when features are correlated but doesn't eliminate irrelevant ones. Elastic Net, the perfect middle ground. It removes the worst features and balances the important ones. Now here's where it gets even crazier. How do we actually implement these in a real-world model? That's exactly what we're about to cover next. And trust me, once you see how easy it is to apply these techniques in Python, you'll wonder why you didn't use them sooner. All right, now we're diving into slide 7, mathematical formulation of regularization. This is where some people start to panic because, let's be real, math formulas can look scary. But here's the thing, you don't need to be a mathematician to understand what's going on here. In fact, I'm going to break this down so simply that by the end of this, you'll not only understand the math, but you'll actually see why it makes total sense. All right, let's set the scene. Imagine you're a music producer and you're mixing a track. You've got vocals, drums, bass, guitar, synths, and all kinds of layers going on. Now, if you just crank up all the volume levels on every track, what happens? The whole thing turns into a distorted, chaotic mess. Nothing sounds clear. The mix is overpowering and unbalanced. So what do? You apply compression, you control the volume, smooth out the extreme peaks, and make sure everything sits well in the mix. That's exactly what regularization does in machine learning. It controls the volume of each coefficient so that no single feature overpowers the model. And the way it does that? With math. But don't worry, it's actually pretty simple. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Let's start with the basic cost function. If you've worked with machine learning before, you know that models try to minimize error. That's their whole job. For something like linear regression, our cost function usually looks like this. J of theta equals the sum of squared differences between the actual values, y sub I, and the predicted values, y hat sub I. This is just the squared error. It's measuring how far off our predictions are from the actual values. The model's job is to find the best parameters t that minimize this error. Now here's the problem. If you don't use regularization, the model will try to force the error as close to zero as possible, even if that means overfitting to noise. This is where regularization comes in. It adds a penalty term to stop the model from going crazy. When we use L1 regularization, we modify our cost function by adding a penalty on the absolute values of the coefficients. J of theta equals the sum of squared differences between the actual values and the predicted values plus lambda times the sum of the absolute values of the coefficients. That second part, L2 Regularization, is what forces the model to shrink some coefficients to zero. This is why L1 performs feature selection. It literally eliminates features that aren't pulling their weight. The larger L is, the stronger the penalty. If L is too big, we remove too many features and risk underfitting. If it's too small, we might still overfit. Now, L2 works a little differently. Instead of penalizing absolute values, it penalizes the squared values of the coefficients. J of theta equals the sum of squared errors plus lambda times the sum of the squared values of all the coefficients. This means that instead of eliminating features completely, L2 just shrinks them down smoothly. It's like turning down the volume instead of muting a track. This is why L2 is better for situations where all features are important, but some just need to be balanced out. ElasticNet is just a combo of both. J of theta equals the sum of squared errors plus lambda 1 times the sum of the absolute values of the coefficients plus lambda 2 times the sum of the squared values of the coefficients. It takes the best of L1 and L2. It removes useless features, L1, but also smooths out the ones that stay, L2. At this point, you might be thinking, okay, I get it, but do I actually need to memorize these formulas? Nope. The key takeaway is this: L1, Lasso, adds a penalty based on absolute values, shrinks some features to 0, feature selection L2, Ridge, adds a penalty based on squared values, shrinks all features but keeps them, ElasticNet, a mix of both, removes useless features but keeps important ones balanced. And the best part? You don't even have to code these formulas from scratch. Scikit-learn already has these built in. You just have to tweak alpha in Python to get the right balance. Now that we've got the math down, the next big question is, how does regularization actually impact a model's performance? What happens when you apply too little or too much regularization? That's exactly what we're covering next. And trust me, what you're about to see might completely change the way you approach model tuning. The aftermath about aftermath, I lose my veers, but you still hear awesome. Now we're stepping into the impact of regularization on model performance, and this is where things start to get really interesting, because now we're not just talking about theory, we're talking about real results. This is the part where regularization either makes or breaks your model. Let me ask you a question. Have you ever seen a model that performs insanely well during training, like 99% accuracy, but then when you test it on new data, it completely flops? Yeah, that's the classic sign of overfitting, and we already know regularization is the fix. But here's the catch. Too much regularization is just as bad as too little. It's like preparing for a test. If you don't study at all, you fail because you don't know the material. But if you try to memorize every single word in the textbook, you still fail because you spent too much time on unnecessary details and couldn't actually apply what you learned. Regularization works the same way. It's all about finding the sweet spot between learning enough and not overcomplicating things. So what happens when you apply regularization? Let's look at two different models. Model A, no regularization. This model is like a student who memorized every single example from the training data. On training data, it absolutely crushes it, 99% accuracy. But when you give it new data, boom, accuracy drops to 70% or worse. Why? Because it was too obsessed with the details of the training set and can't generalize to anything new. Model B with regularization. Now we apply L1, L2, or ElasticNet to Model B. The training accuracy might drop a little, maybe from 99% to 90%, but the real magic happens on new data. The validation accuracy jumps up because now, instead of memorizing, the model actually understands the data. Let's put some numbers on it. Without regularization, training accuracy were 95%, validation accuracy almost 70%. With regularization, training accuracy, 90%, validation accuracy, abras 85%. See that? We sacrificed a little bit of training accuracy to get way better generalization on new data. This is where we talk about the bias-variance trade-off, which is basically the balancing act every ML engineer has to deal with. No regularization, low bias, high variance. The model learns too much, including noise, and doesn't generalize. Too much regularization. High bias, low variance. The model is too simple and doesn't learn enough, leading to underfitting. Balanced regularization. Just right. The model learns what's important while ignoring irrelevant details, leading to better performance. It's like Goldilocks. Too little regularization, and your model is too complex. Too much, and it's too simple. You need to find the just right amount. So how do you actually tune regularization for the best performance? This is where hyperparameter tuning comes in. We don't just guess the best lambda or alpha if you're using scikit-learn. Instead, we use methods like cross-validation, testing different values of lambda on multiple datasets, grid search and random search, automating the process of finding the best regularization strength. But here's the crazy part. Regularization doesn't just improve accuracy, it also makes models more stable and interpretable, especially when working with high-dimensional data. Now that we've seen why regularization improves performance, the next step is actually choosing the right technique for different types of models, which is exactly what we're covering next. Because trust me, using the wrong type of regularization can do more harm than good. And that's something you don't want to get wrong. Are you ready to getting into choosing the right regularization technique? And this is where things really matter. Because knowing what regularization is one thing, but knowing when to use which technique, that's what separates average data scientists from great ones. Let's set the scene. Imagine you're a mechanic and a customer brings you a car that's not working properly. You pop open the hood and you see a total mess. Now, you've got a whole set of tools in your toolbox. But here's the thing, if you use the wrong tool, you might not just fail to fix the problem, you might actually make it worse. Regularization is exactly like that. You've got L1, Lasso, L2, Ridge, and Elastic Net. But if you use the wrong one for your problem, your model could completely fail. So how do you know which one to pick? When to use? L1 regularization. Lasso, L1 is the minimalist, the tool you use when you need to reduce the number of features in your dataset. Use L1 regularization when you have a huge dataset with too many irrelevant features. You need to perform feature selection. L1 will automatically shrink some coefficients to 0 and remove unnecessary inputs. You're working in fields like genetics, text processing, or finance, where most features don't matter, but a few critical ones do. Let's say you're predicting house prices and you have 100 different features, everything from the number of bedrooms to whether the house is painted blue. But here's the thing, only 5-10 of those features actually matter. L1 will automatically eliminate the useless ones, leaving you with a cleaner, more interpretable model. But L1 has one big drawback. If two features are highly correlated, Lasso might randomly eliminate one of them, even if they're both important. And that's where L2 comes in. L2 is the strict coach. It doesn't delete features, but it smooths them out so that no single feature dominates the model. Use L2 regularization when all your features matter, but some of them are too dominant. Your dataset has multicollinearity, meaning many features are highly correlated and could cause instability in your model. You're working with image processing, speech recognition, or deep learning, where every input has some relevance, but you don't want certain features overpowering everything. Let's say you're building a model to predict employee performance at a company. You have features like years of experience, education level, and certifications. Now, years of experience and certifications might be highly correlated, but you don't want to delete one. Instead, L2 balances them so that the model considers both without letting one dominate too much. But L2 never eliminates features, even if they are completely useless. That's where ElasticNet comes in. ElasticNet is the best of both worlds. It removes useless features, like L1, while also balancing the ones that stay, like L2. Use ElasticNet when you have a ton of features and some need to be removed while others need to be balanced. Your dataset has highly correlated features, but you still want to perform feature selection. You want a more stable version of L1. ElasticNet won't randomly eliminate one correlated feature over another. Imagine you're building a fraud detection system. You have thousands of transaction features, some of which are completely useless, while others matter a lot. You don't just want to delete features. You want to find the key fraud indicators and balance them properly. ElasticNet does that. So, here's the ultimate cheat sheet for picking the right regularization technique. Use L1, Lasso, when you need to reduce the number of features. Use L2, Ridge, when all features matter, but some need to be controlled. Use ElasticNet when you need a mix of both, removing useless features but balancing the important ones. But here's the thing, how do you actually tune these techniques to make sure you're using the right amount of regularization? Because if you set your regularization strength too high, your model will be too simple and underfit. If you set it too low, your model will still overfit. That's exactly what we're going to cover next. How to fine-tune regularization using hyperparameter tuning and cross-validation. And trust me, you don't want to just guess these values, because the right tuning can make or break your model's performance. All right, now it's time to take everything we've learned and actually apply it in a real-world scenario. Because let's be honest, understanding regularization is one thing, but knowing how to use it in a model is what really matters. So let's imagine a situation. You're working on a machine learning project. Maybe it's predicting house prices, customer churn, or fraud detection. Your model seems to be working fine during training. It's hitting high accuracy, low error, everything looks great. But then the moment you test it on new data, the performance completely drops. That's when you know you've got an overfitting problem. And at this point, you have two choices. One, you can ignore it and hope for the best. Good luck with that. Or two, you can do what any good machine learning engineer does and apply regularization to fix it. And here's the best part. It takes just a few steps to do it. Now, for those of you who want to follow along with the code, I've put everything you need in the video description so you can download it and test it out yourself. But for now, let's walk through how this works conceptually. First, when you're dealing with a machine learning problem, you always start by loading and preparing your data. This means getting your data set, cleaning it up, and splitting it into a training set and a test set. Because if you don't have a proper test set, you'll never know if your regularization is actually improving performance. Next, you need to choose which type of regularization to apply. If you have a data set with way too many irrelevant features and you suspect some of them are just adding noise, you're going to use L1 regularization, also known as Lasso. This will literally eliminate useless features, forcing the model to focus only on what matters. But if you're working with a dataset where every feature is important, but some of them are just a little too dominant, then you want L2 regularization, or Ridge. This doesn't remove features, but it smooths them out, making sure no single feature overpowers the others. And then, if you want the best of both worlds, you use ElasticNet, which is a combination of L1 and L2. It removes the worst features, but also balances the ones that stay, giving you a cleaner and more stable model. Once you've chosen which regularization method to use, the next step is to actually train your model with regularization applied. And this is where things get really interesting, because when you compare the results before and after applying regularization, you'll notice something fascinating. At first, your model might actually perform slightly worse on training data. It might drop from 99% accuracy to 90% accuracy. And you might think, wait, why am I making my model worse? But then, when you test it on new data, you see the real magic happen. Your model, which was once overfitting like crazy, now actually performs better in the real world. Instead of failing on unseen data, it makes accurate predictions because it's learned to generalize, and that right there is the entire point of regularization. You are intentionally sacrificing a little bit of training accuracy in order to gain much better performance on real-world data. Now, here's where things get even more interesting. How do you know how much regularization to apply, because if you apply too little, your model will still overfit. But if you apply too much, your model might become too simple and underfit instead. And that's exactly what we're going to cover next: how to fine-tune regularization using hyperparameter tuning and cross-validation. Because here's the thing, guessing the right value for regularization is a terrible strategy. If you want a model that actually performs well, you need a systematic way to find the best regularization strength. And that's what we're diving into next. Let's set the scene. Imagine you're working as a data scientist for a real estate company, and your job is to build a model that predicts house prices. You've collected tons of data: square footage, number of bedrooms, location, crime rates, school ratings, you name it. So you throw all of this into a linear regression model, hit train, and boom, you get a near perfect fit on your training data. But then when you test it on new properties, your predictions are completely off. Prices are all over the place. The model isn't generalizing at all. What went wrong? Your model overfit the training data. It learned every tiny detail, including random fluctuations and noise, instead of focusing on the real patterns. And this is exactly why regularization is critical in linear regression. Linear regression might seem like a simple algorithm, but it's surprisingly prone to overfitting, especially when you have too many features. The more variables you add, the easier it is for the model to pick up on irrelevant patterns. Your features are highly correlated. If two features contain similar information, the model can become unstable and assign huge coefficients to both. Your data contains noise or outliers. If you have messy data, a standard linear regression model will try to fit every little detail even when it shouldn't. Without regularization, your model's coefficients can explode, meaning some variables will get way too much importance, while others might be completely ignored. So how do we fix this? This is where L1, Lasso, and L2 Regularization come in. Instead of letting the model go crazy and assign huge coefficients to certain variables, we add a penalty to control how large the coefficients can get. L1 regularization, Lasso, in linear regression. If you have too many features, Lasso will eliminate the least important ones, reducing complexity. L2 regularization, RIG, in linear regression. If you have highly correlated variables, RIG will balance them out, preventing instability. Elastic net. If you need both feature selection and balance, elastic net is the way to go. By adding regularization, your model stops memorizing noise and starts learning the actual patterns. Let's go back to our real estate model. Imagine we have a data set with 100 different features. Things like square footage number of bedrooms distance to the nearest school, crime rate, year built, and 95 other things. Now, some of these matter a lot, like square footage. Others? Not so much. Maybe number of trees in the backyard isn't exactly a key predictor of house prices. A regular linear regression model would try to fit everything, including the useless details. But if we apply L1 regularization, Lasso, it will automatically remove the least important variables, simplifying the model and making it more interpretable. On the other hand, if we apply L2 regularization, RIG, it won't remove features, but it will make sure the model doesn't rely too heavily on any single variable, preventing one dominant factor from taking over. And if we're not sure which one to use, we can go with elastic net, which gives us the best of both worlds. Regularization is non-negotiable in linear regression, especially when you have lots of variables and you need to remove the unimportant ones. Lasso. Your features are highly correlated and you need to balance them rich. You want a blend of both, keeping the best features and smoothing the rest. Elastic net. And Now that we've seen why regularization is so critical in linear regression, the next big question is what happens when we apply it to classification models? Because in logistic regression, regularization works a little differently, but trust me, it's just as important, and that's exactly what we're about to dive into next. I like to move it now. We're moving direct into the wonderful world of regularization in logistic regression, and this is a big one. Because while most people associate regularization with linear regression, it's just as critical, if not more so, when we're working with classification models. Let's set the stage. Imagine you're building a fraud detection system for a bank. Your model needs to classify transactions as either fraudulent or legitimate. You collect tons of data, transaction amounts, location, time of day, previous transaction history, and so on. So you decide to train a logistic regression model. And at first it looks great. It's classifying fraud with high accuracy on your training data. The bank executives are happy, you're feeling like a genius until you deploy it. And then it fails hard. Suddenly it's flagging way too many legitimate transactions as fraud while also missing actual fraudulent ones. Customers are complaining, transactions are getting blocked for no reason, and now the bank is losing money because of false positives. What happened? Overfitting. Your logistic regression model memorized too much from the training data. It learned specific patterns instead of general rules. So when faced with new transactions, it completely breaks down. And this is exactly why we need regularization in logistic regression, to prevent the model from learning too much noise and to help it generalize to new data. Unlike linear regression, which predicts continuous values, logistic regression predicts probabilities. It gives a score between 0 and 1 that determines whether something belongs to one class or another. But here's the problem. If your data set has too many features, or if some of them are highly correlated, your logistic regression model can go crazy. It will assign huge coefficients to certain features, making its predictions unstable and highly dependent on just a few variables. That's where L1 and L2 regularization come in. Just like in linear regression, we can apply L1 regularization, Lasso. Shrink some coefficients all the way to 0, effectively performing feature selection, L2 regularization, Ridge. Shrinks all coefficients without eliminating them, making the model more stable. Elastic net, a combination of both, removing some features while balancing the importance of the rest. But here's where it gets interesting. Regularization in logistic regression doesn't just prevent overfitting, it also improves interpretability. Imagine you're working in healthcare, trying to build a model that predicts whether a patient has a disease based on medical records. You have hundreds of lab test results, genetic factors, and lifestyle choices as inputs. If you train a logistic regression model without regularization, it might learn from every single variable, even the ones that don't actually contribute to the disease. This makes it harder to explain which factors truly matter in making a diagnosis. But if you apply L1 regularization, Lasso, it will eliminate irrelevant factors, leaving you with a cleaner, more interpretable model that doctors can actually trust. Or, if some of the lab test results are highly correlated, L2 regularization, Ridge, will balance them out, so that no single test dominates the decision-making process. Let's switch gears to another example. Spam email detection. Say you're building a classifier that predicts whether an email is spam or not based on the words it contains. You extract thousands of features from emails, word frequencies, sender reputation, formatting patterns, and more. Without regularization, your logistic regression model might focus too much on a handful of words, overfitting to specific spammy phrases. But if you apply L1 regularization, it will automatically select the most important words while ignoring the rest, making the model simpler and faster. Or, if you use L2 regularization, it will make sure all features contribute proportionally rather than letting a few dominate the decision-making process. And if you're not sure which one to use, Elastic Net is your best bet because it combines the power of both. So, what's the bottom line here? Logistic regression models can overfit just like linear regression models, especially when working with high-dimensional data. L1 regularization, Lasso, helps with feature selection, removing unnecessary inputs. L2 regularization, Ridge, prevents instability when features are correlated. Elastic Net gives you the best of both worlds, removing useless features while balancing the rest. And now that we've seen how regularization improves classification models, the next big question is, how does it work in deep learning? Because when you're dealing with neural networks, overfitting is an even bigger problem, and regularization takes on a whole new role. That's exactly what we're diving into next. Awesome. Now we're stepping to regularization in neural networks, and this is where things get even more exciting. Because if you thought overfitting was bad in regression models, just wait until you see what happens in deep learning when you don't apply regularization. Let's set the stage. Imagine you're training a neural network to recognize handwritten digits, kind of like the ones banks use to read checks. You collect thousands of images, label them, and build a deep neural network with multiple layers to classify the numbers. You train it on your dataset, and the accuracy starts shooting up 80%, 85%, 90%. Eventually, it reaches 99%. You're thinking, I've built a masterpiece. This model is a genius. But then you test it on new images, and suddenly the accuracy drops to 65%. What happened? Your network didn't learn how to recognize numbers. It memorized your training images, every single pixel pattern, every little noise variation. It stored them all like a giant lookup table instead of understanding the actual shapes of digits. And that, my friends, is overfitting at its worst. This is exactly why regularization is absolutely critical in neural networks, because without it, deep learning models memorize the training data instead of generalizing. Neural networks are powerful, but they have a major weakness. They have too many parameters. Think about it. A deep learning model with millions of neurons and connections can easily learn every little detail in the training data, even the ones that don't matter. And the result? It performs amazingly well on training data. It fails miserably on new data. This is why regularization is even more important in deep learning than in simpler models like logistic or linear regression. Regularization in deep learning is a bit different from L1 and L2 in regression. We use techniques specifically designed for neural networks to stop them from memorizing everything. Here are the 4 most common methods used to regularize neural networks. Dropout is one of the most powerful and widely used regularization techniques in deep learning. Here's how it works. Imagine you're training a basketball team, and every time they practice, you randomly bench different players. One day your star player sits out. The next day, another one is out. This forces everyone to learn how to contribute instead of just relying on a few key players. That's exactly what dropout does to neural networks. During training, it randomly drops neurons from the network, forcing the model to learn redundant patterns instead of memorizing specifics. By the time training is done, the model has learned robust, generalizable features instead of just overfitting to the training data. Just like in linear and logistic regression, L1 and L2 regularization can also be applied to neural networks, except here they're applied to the weights of the network. One regularization forces some weights to become exactly 0, simplifying the network and helping with feature selection. L2 regularization, also known as weight decay, shrinks all weights smoothly, preventing large values from dominating. In deep learning, L2 is used more often because it helps stabilize the model without making it too sparse. Early stopping is one of the simplest and most effective ways to prevent overfitting. Here's how it works. Imagine you're cooking a steak. You don't want to undercook it, but you also don't want to burn it. So what do? You watch carefully and take it off the heat the moment it's perfectly done. Early stopping works exactly like that. Instead of training your neural network for too long, you monitor its performance on a validation set. The moment the validation loss starts getting worse instead of better, you stop training right at the sweet spot before overfitting kicks in. Batch normalization is another powerful regularization technique, but it works a little differently. Instead of reducing complexity, it keeps the network stable by making sure each layer gets properly scaled inputs. Think of it like a DJ mixing audio. If some instruments are way too loud and others are too quiet, the song doesn't sound right. Batch normalization balances the inputs at every layer, ensuring that learning happens at a steady rate and preventing the network from becoming too sensitive to any particular feature. Let's say you're building an image recognition model to classify pictures of dogs and cats. If you don't use regularization, the model might memorize specific details of the training images, like the background, lighting, or specific textures of fur. So when you give it a new image, it might fail because it was relying on details that had nothing to do with whether it's a dog or cat. But if you apply dropout, L2 regularization, and batch normalization, your model is forced to learn the actual distinguishing features like ear shape, eye position, and nose structure instead of memorizing specific training examples. Regularization in neural networks is not optional. It's absolutely necessary if you want a model that actually works in the real world. Dropout prevents over-reliance on certain neurons by randomly disabling them. L2. Regularization, weight decay, prevents weights from growing too large and keeps the model balanced. Early stopping makes sure you don't train too long and start overfitting. Batch normalization keeps input stable so the network learns efficiently. And now that we've covered how regularization keeps neural networks under control, the next big question is, how do we apply it to tree-based models like decision trees and random forests? Because when it comes to tree models, regularization looks completely different. But trust me, it's just as important. It is time to moving into regularization in decision trees, and this is where things get really interesting. Because unlike linear models and neural networks, decision trees have a completely different way of overfitting, and that means they also need a completely different approach to regularization. Let's set the stage. Imagine you're working on a customer churn prediction model for a telecom company. You've collected tons of data, customer call duration, payment history, service complaints, and more. You decide to train a decision tree model, and at first it looks fantastic. It reaches 100% accuracy on the training data. That's right, 100% accuracy. You're thinking, this is incredible. I've built the perfect model. But then, when you test it on new customers, it completely fails. The predictions are all over the place. What happened? Your decision tree memorized every single detail of the training data instead of learning general patterns. Instead of figuring out why customers churn, it learned specific conditions that only apply to your training set. And this is the exact reason why regularization is critical in decision trees, because without it, they tend to overfit like crazy. Decision trees are very powerful because they can capture complex patterns in data, but that power is also their biggest weakness. Here's why decision trees overfit so easily. They keep splitting until they perfectly classify every training point. This means the tree grows too deep, making it too specific to the training data. They can pick up noise instead of real patterns. If there's random noise in the dataset, an unrestricted decision tree will learn it as a rule, which is terrible for generalization. They don't naturally generalize well. Unlike linear models, which assume relationships between features, decision trees learn purely from the data, which means if they overfit, they don't transfer well to new data. So how do we fix this? Regularizing decision trees is different from regularizing linear models. Instead of L1 or L2 penalties, we use techniques that control how deep the tree grows and how much detail it captures. There are three main ways to regularize a decision tree. Pruning is like trimming a bonsai tree. You cut off unnecessary branches so the tree doesn't grow too wild. There are two main types of pruning. Pre-pruning, stopping early. Setting a maximum depth so the tree never grows too deep in the first place. Post-pruning, trimming after training, growing the tree fully, then removing branches that don't add much value. For example, if a branch only applies to 1 or 2 data points, it's probably just memorizing noise, so we cut it off. Another way to prevent overfitting is to limit how deep the tree can grow. Think of it like setting rules for a debate. If you let someone argue for hours, they'll start making ridiculous, overly specific claims. But if you limit the time, they're forced to focus on the most important points. In decision trees, we do this by setting a max depth. If we say max depth number 5, the tree can only go 5 levels deep, preventing it from getting too detailed. This forces the model to focus on the most important splits, instead of trying to classify every tiny variation in the training data. Another problem with decision trees is that they will keep splitting as long as they can, even if there's barely any data left in a branch. This is where we set a rule like min samples, split just 10. The tree must have at least 10 samples in a branch before it can split. Min samples, leaf. 5. A final leaf must have at least 5 data points, so we don't end up with leaves that only apply to 1 or 2 specific cases. This is like saying, we need at least 10 people in a focus group before we make any conclusions. If there's only one person, it's probably not a real trend. It's just noise. Let's say you're working at a bank, building a loan approval model. Without regularization, the decision tree might split based on every single tiny detail, like whether the person applied for a loan on a Wednesday or what time of day they applied. These details are random noise, not real trends. But if you apply pruning, max depth limits, and minimum samples per split, the tree focuses on the bigger picture. Things like credit score, income, and debt-to-income ratio instead of irrelevant details. This makes the model more reliable, and it performs better on new applicants. Decision trees are powerful, but they're also prone to overfitting. Pruning cuts off unnecessary branches, so the tree doesn't memorize noise. Setting a maximum depth forces the tree to focus on the most important splits. Minimum samples per split ensures the model doesn't create rules based on too few examples. And now that we've seen how regularization works in decision trees, the next question is, what happens when we use ensembles, like random forests and gradient boosting? Because when you combine multiple decision trees, regularization becomes even more critical, and trust me, it works in a completely different way. Now we're moving into support vector machines, SVMs, and this is where regularization takes on a slightly different role. Up until now, we've talked about regularization in models like linear regression, decision trees, and neural networks, where the main goal was to control model complexity and prevent overfitting. But when it comes to SVMs, regularization isn't just about complexity, it's about finding the perfect balance for decision boundaries. So let's step back and understand what's happening here. SVMs are all about finding the optimal boundary between different classes in your data. If you're trying to classify emails as spam or not spam, the SVM is looking for a hyperplane that best separates the two groups. The key idea in SVMs is that the best boundary isn't just one that separates the data, but one that does so with the maximum possible margin. The larger the margin, the more confident the model is in its classification. But here's where things get tricky. If your model only focuses on perfectly separating the training data, it can end up with a very tight, overly specific decision boundary, which means it's overfitting. Instead of learning a generalizable rule, it starts treating every tiny variation in the training data as significant. This is where regularization in SVMs comes in. The C parameter is the key regularization control in SVMs. It determines how much flexibility the model has in allowing some misclassification. Think of it as the strictness of the boundary. If C is very large, the model is forced to classify every training point correctly, meaning the boundary is very rigid, which can lead to overfitting. If C is small, the model allows some misclassifications but creates a smoother, more general boundary, reducing overfitting. This is exactly like having a strict teacher versus a relaxed teacher. A strict teacher forces students to memorize every detail, but when they face a new question in an exam, they struggle. A relaxed teacher allows some mistakes during learning, but the students develop a deeper understanding and do better in real-world tests. So, the key takeaway here is that choosing the right value of C is critical. Too high, and your model memorizes training data. Too low, and it's too soft, leading to underfitting. Ow. Things get even more interesting when we introduce the kernel trick. Because not all data is linearly separable. We sometimes need to transform the data into a higher dimensional space where a clear boundary exists. But if you don't apply proper regularization while using a complex kernel, the model can easily overfit, just like in deep learning. This is why SVM regularization isn't just about tuning C. It's also about choosing the right kernel and controlling how complex the transformation is. If you get it right, SVMs are one of the most powerful classification models out there. If you get it wrong, they can become unstable and unreliable in real-world applications. Now, let's take this one step further. We've talked about regularization in SVMs, but what happens when we move beyond a single model and start working with ensemble methods like random forests and gradient boosting? That's exactly what we're going into next. Now we're stepping into ensemble models, and this is where regularization takes on an entirely different role. Unlike individual models, ensemble methods don't just overfit in one way, they overfit in layers. If you don't control complexity properly, ensemble models can become way too powerful and start capturing every single detail from the training data, making them completely unreliable on new data. So let's break this down. First, let's talk about random forests. This is an ensemble method that combines multiple decision trees. The key benefit of a random forest is that it's less prone to overfitting than a single tree, but that doesn't mean it's immune to it. If each tree in the forest is too complex, the entire model will still memorize the training data instead of learning general rules. The way we regularize random forest is by limiting tree depth, so that no single tree grows too deep and memorizes patterns. Setting a minimum number of samples per leaf, which forces the model to generalize over more data points before making a split. Using feature subsampling so that each tree sees only a subset of features, preventing it from relying too much on any single variable. Now, let's shift to gradient boosting, which includes models like XGBoost, LightGBM, and CatBoost. Unlike random forests, which train all trees independently, boosting methods train trees sequentially, where each new tree corrects the mistakes of the previous ones. This makes them incredibly powerful, but also extremely prone to overfitting. If you don't regularize gradient boosting, it keeps correcting errors to the point where it memorizes noise instead of actual patterns. To prevent this, we use learning rate adjustments, so that each tree makes smaller, more controlled updates, L1 and L2 penalties on tree weights, which prevent overly complex splits, early stopping, which halts training once validation performance stops improving. The key idea here is that boosting methods don't just need regularization, they depend on it. If you don't properly tune hyperparameters like the learning rate, number of trees, and subsampling, you'll end up with a model that looks great on paper but completely collapses on new data. This brings us to the next big challenge. How do we actually fine-tune regularization? Because it's one thing to apply it, it's another to get the balance just right. That's exactly what we'll cover next. Now we're getting into one of the most important aspects of regularization, fine-tuning it properly. Because, let's be real, just applying regularization isn't enough. If you don't tune it correctly, you could either kill your model's performance by over-restricting it, or you could fail to stop overfitting altogether, and that's exactly what we're going to fix here. Every regularization technique, whether it's L1, L2, dropout, early stopping, or tree pruning, depends on finding the right balance. And that's where hyperparameter tuning comes in, because let's face it, guessing values is not a strategy. If you're randomly picking values for lambda, dropout rate, or tree depth, you're basically gambling with your model's accuracy. So how do we do it properly? There are three main approaches, and each has its strengths. First, there's grid search, which is the brute force approach. It tests every possible combination of hyperparameters, systematically going through each one. It's exhaustive, but the problem is it can be extremely slow, especially when you have multiple parameters to tune. Then there's random search, which is much faster. Instead of testing every combination, it selects a random subset of values to test. And here's the surprising part. Research shows that for many problems, random search performs just as well as grid search, but in a fraction of the time. That's because not every hyperparameter matters equally, so testing everything is often overkill. But the real game changer is Bayesian optimization. Instead of randomly picking values or checking everything, Bayesian optimization learns from past trials to intelligently suggest the best hyperparameters to try next. It's like hiring a professional chef instead of trying every single spice yourself. It knows what's likely to work based on what's been tested before. So what does this look like in practice? Imagine you're working with a deep learning model and you need to tune dropout rate, L2 regularization strength, and learning rate. Instead of guessing, you run Bayesian optimization, and within a few hours, you've found the perfect balance, one that prevents overfitting without killing performance. The takeaway here is simple. Regularization only works if you tune it properly. And tuning isn't about intuition. It's about systematically optimizing hyperparameters to get the best possible model. But now that we know how to fine-tune regularization, the next big question is, how do we actually measure whether it's working? Because if you don't evaluate regularization properly, you might think you've improved your model when you've actually made it worse. That's exactly what we'll cover next. Now we're diving into one of the most important techniques in machine learning, cross-validation, and how it connects with regularization. Because let's be honest, applying regularization is one thing, but how do you know if it's actually working? That's exactly what cross-validation helps us figure out. So let's step back for a moment. Imagine you're training a machine learning model. You split your data into a training set and a test set, train your model, and check the performance on the test set. If the accuracy is high, you might think, great, I'm done. But there's a huge problem with this approach. It only evaluates the model on a single split of the data. What if that particular test set was too easy? Or what if it contained rare edge cases that don't reflect real-world data? One test set isn't enough to judge the true performance of a model. And this is exactly where cross-validation comes in. Cross-validation helps us measure how well our model truly generalizes by splitting the data into multiple training and validation sets, training the model on different portions, and testing it on different portions each time. Instead of relying on a single test split, we evaluate the model across multiple folds of the data. Now let's connect this to regularization. Regularization is all about preventing overfitting, but the tricky part is finding the right level of regularization. If you regularize too little, the model still overfits. If you regularize too much, the model becomes too simple and underfits. So how do you find the perfect balance? This is exactly where cross-validation comes in. Instead of just testing regularization on a single split of data, we test it on multiple folds, which gives us a more reliable measure of performance. Let's say you're training a logistic regression model with L2 regularization. If you pick a random lambda value and test it on one test split, you might think it works well. But when you run cross-validation, you might see that performance varies wildly across different data folds, meaning the regularization strength isn't optimized. By using cross-validation to test different values of lambda, you get a clearer picture of which regularization setting is truly working across all the data, not just one test set. This is also critical for deep learning models. Let's say you're tuning dropout rates in a neural network. If you just test one setting on a single test split, you might miss the bigger picture. But if you cross-validate different dropout rates across multiple data folds, you can find the setting that consistently improves generalization. Now, let's take it one step further. Cross-validation doesn't just help us evaluate how much regularization to apply, it also helps us decide which type of regularization works best. Let's say you're working with a high-dimensional data set with thousands of features. You're not sure if you should use L1 regularization, Lasso, to remove features, or L2 regularization, Ridge, to balance them out. By running cross-validation on both approaches, you can compare their stability and performance across multiple folds, helping you make the right choice based on actual data, not just intuition. This is why cross-validation and regularization go hand in hand. Cross-validation helps answer the biggest questions in model tuning. How much regularization is too much? Is my model actually generalizing, or is it just lucky on a single test split? Which type of regularization works best for my data? And the key takeaway here is that if you're not using cross-validation to test your regularization settings, you're not truly optimizing your model. One test split isn't enough. You need to test across multiple folds to ensure your model is actually learning generalizable patterns, not just fitting to a single dataset split. Now that we've covered why cross-validation is so critical, the next big question is, how does regularization actually impact real-world applications? Because at the end of the day, this isn't just about optimizing test scores, it's about making sure AI models work in industries like healthcare, finance, and autonomous systems. And that's exactly what we'll dive into next. Now we're stepping into one of the most powerful benefits of regularization, feature selection. Because sometimes the problem with machine learning models isn't just overfitting, it's too many unnecessary features cluttering the model, making it more complex than it needs to be. Think about it this way. Imagine you're trying to predict house prices and your data set contains hundreds of features: square footage, number of bedrooms, year built, neighborhood crime rates, and even things like the color of the front door. Now, common sense tells you that the color of the front door probably doesn't matter for predicting prices. But if you don't remove irrelevant features, your model might still try to find a pattern in them, and that's exactly where feature selection using regularization comes in. At first glance, you might think the more features, the better, right? More data means a more informed model, but that's not how it works. When you have too many features, the model becomes unnecessarily complex, increasing the risk of overfitting. Some features are correlated with each other, leading to redundancy. Noise and irrelevant features distract the model, reducing performance. This is especially problematic in high-dimensional datasets like genetics, text processing, and finance, where you might have thousands of features, but only a small number of them actually matter. Instead of just removing features manually, regularization can automatically select the most important ones for you. The two most common ways regularization helps with feature selection are through L1 regularization, Lasso, and elastic net. First, let's talk about L1 regularization, or Lasso regression. L1 regularization doesn't just shrink feature weights like L2 does, it actually forces some of them to become exactly zero. That means it's automatically removing irrelevant features from the model. Let's go back to our house price prediction example. If you apply L1 regularization, it might reduce the weights of features like color of the front door or number of trees in the backyard down to zero, completely removing them from the equation. This is extremely useful because instead of manually deciding which features to keep, Lasso does it for you. Now, L1 regularization has one drawback. It can sometimes be too aggressive, removing features that might still have some importance. That's where elastic net regularization comes in. Elastic net is a combination of L1 and L2 regularization. It removes irrelevant features like L1, but also keeps some balance like L2, preventing the model from being too aggressive. This is especially useful in datasets where you have many correlated features. Lasso might randomly pick one and remove the rest, but ElasticNet preserves the relationships between them, keeping a better overall model structure. Now, let's apply this to a real-world problem. Imagine you're working on a medical diagnosis model that predicts whether a patient has heart disease. Your dataset contains hundreds of biomarkers, blood pressure, cholesterol levels, genetic markers, and even some irrelevant factors like hair color and height. If you train a model without feature selection, it might learn patterns that don't actually matter, like an accidental correlation between hair color and heart disease simply because the training set happened to contain more patients with dark hair. But if you apply L1 regularization, the model automatically removes useless features, keeping only the most relevant medical indicators. This is exactly why feature selection using regularization is so powerful. It helps the model focus on the most important patterns rather than getting lost in irrelevant noise. One of the biggest mistakes in machine learning is assuming that more features means a better model. In reality, more features often make a model worse by adding unnecessary complexity and noise. Regularization helps simplify models by removing irrelevant features, making them more interpretable, especially in fields like healthcare and finance, where understanding the reasoning behind AI predictions is crucial. More efficient, reducing computational costs and training time, which is important for large-scale AI models. More generalizable, because they aren't distracted by unnecessary details, leading to better real-world performance. And now that we've seen how regularization helps with feature selection, the next big question is, how is regularization shaping the future of AI? Because as machine learning models get bigger and more complex, new forms of regularization are emerging to keep them under control. Now we're diving into one of the biggest challenges in machine learning, model complexity, and how regularization helps keep it under control. Because here's the truth. Machine learning models are getting bigger, deeper, and more complex every year. And while complexity can increase power and accuracy, it also brings a serious risk of overfitting, instability, and inefficiency. So let's break it down. At first, it might seem logical to think that a more complex model is always better. After all, deeper neural networks, more features, and more parameters should mean better accuracy, right? Not exactly. When a model is too complex, it doesn't just learn meaningful patterns, it starts memorizing every detail in the training data, including noise and random fluctuations. This is why a deep neural network with millions of parameters can sometimes perform worse than a simple logistic regression model. The challenge is finding the right level of complexity, one that's powerful enough to capture meaningful relationships, but simple enough to generalize to unseen data. And this is exactly where regularization plays a crucial role. Regularization helps limit unnecessary complexity by imposing constraints on the model. The goal isn't to make the model weaker, it's to make sure it's learning only what matters instead of memorizing noise. Different types of models require different approaches to control complexity. For models like linear regression and logistic regression, complexity comes from the number and magnitude of feature weights. If a model assigns very high weights to certain features, it often means it's relying too much on those features, which can lead to overfitting. L1 regularization, Lasso, forces some feature weights to become exactly zero, effectively removing less important features. L2 regularization, Ridge, smooths out large weights, preventing any one feature from dominating the model. By applying L1 or L2 regularization, we control complexity by ensuring that only the most relevant features contribute to predictions. Deep learning models are notorious for becoming too complex. With millions or even billions of parameters, they can learn every tiny detail in the training data, including irrelevant patterns. Regularization techniques like dropout and weight decay help keep complexity under control. Dropout randomly disables neurons during training, preventing the network from relying too much on specific connections. Weight decay, L2 regularization, ensures that large weight values are penalized, keeping the network stable and reducing the risk of overfitting. This allows neural networks to learn the core patterns in data without memorizing every tiny detail. In tree-based models like decision trees, random forests, and gradient boosting, complexity is controlled by limiting how deep the trees can grow and how many splits they can make. If a decision tree is allowed to grow unrestricted, it will keep splitting until it perfectly classifies every training example, which is a guaranteed way to overfit. Regularization methods for tree-based models include pruning, removing unnecessary branches that don't contribute much value, max depth restriction, limiting how deep the trees can go, minimum samples per leaf, ensuring each decision split is based on enough data points to be meaningful. For gradient boosting models like XGBoost or LightGBM, additional regularization techniques include learning rate tuning to ensure each tree contributes a small, controlled improvement, subsampling, so that each tree is trained on a random subset of data, preventing overfitting. These methods keep tree models interpretable and generalizable, while still allowing them to capture meaningful patterns. Now, let's apply this to a real-world example. Imagine you're developing an AI system for diagnosing diseases from MRI scans. A deep learning model with millions of parameters could easily learn to detect hospital-specific image artifacts, like subtle differences in scanner resolution or lighting, rather than actual disease markers. If the model overfits to these hospital-specific details, it won't work when tested on MRI scans from a different hospital. By applying dropout, weight decay, and cross-validation across multiple hospitals, you ensure the model learns real medical patterns, not just quirks of the training data. This is why controlling model complexity with regularization is critical in real-world AI applications. It prevents models from becoming too specialized for their training data, ensuring they generalize properly to new cases. At the end of the day, the most powerful AI models aren't just complex, they're optimized for the right level of complexity. Regularization helps reduce unnecessary complexity so that models don't memorize noise, improve generalization so models work on new, unseen data, enhance interpretability by keeping models simple enough to understand. And now that we've seen how regularization keeps models under control, the next big question is, where is regularization headed in the future? Now we're diving into why regularization is critical for achieving generalization, because here's the thing, a good machine learning model doesn't just work on the data it's trained on, it works on new, unseen data as well. And that's where generalization comes in. At its core, generalization is about building a model that isn't just accurate, it's reliable, flexible, and robust in real-world scenarios. If a model performs perfectly on training data but fails on test or real-world data, then it hasn't generalized, it's just overfitted. And that's a common trap when models aren't regularized properly. Let's break it down. Regularization techniques like L1 and L2 penalties are specifically designed to prevent a model from becoming too complex or too specific to the training data. They achieve this by adding a penalty to the loss function, which discourages overly large or complex parameter values. By limiting the complexity of the model, regularization ensures that the model focuses on underlying patterns in the data rather than memorizing specific details or noise. This is what allows the model to generalize to unseen data, which is critical in real-world applications. For example, imagine you're building a fraud detection model. Without regularization, the model might learn specific patterns unique to the training dataset, like the transaction timestamps or account numbers that don't appear in new data. But with regularization, the model is forced to focus on the general patterns of fraudulent behavior, like unusual transaction amounts or geographic inconsistencies. Studies have shown that regularized models can reduce test error rates by up to 20% compared to unregularized counterparts. This is because regularization helps strike a balance between bias and variance, ensuring that the model isn't too simple, underfitting, or too complex, overfitting. Let's take an example of L2 regularization, RIDGE. When you apply L2 regularization to a model, it smooths out the parameter values, ensuring that no single feature dominates the prediction process. This improves the model's ability to handle variations in test data, leading to better performance on validation datasets. Image classification. In computer vision tasks, regularization techniques have significantly improved accuracy on validation datasets. For instance, models trained with dropout and weight decay can generalize better to unseen images, achieving over 90% accuracy on challenging datasets. Natural language processing. In NLP, regularization has been crucial in improving the performance of large-scale language models. By applying techniques like dropout, L2 regularization, and data augmentation, these models have reduced perplexity scores, a measure of prediction quality, by 15–30%, leading to more reliable text generation and sentiment analysis. At the end of the day, the goal of machine learning isn't just to build models that perform well on training data, it's to create systems that work in the unpredictable, messy real world. Regularization is the key to achieving that. So the next time you train a model, don't just aim for high accuracy on the training set. Instead, ask yourself, can this model handle new data? Does it generalize? And if the answer isn't clear, regularization might just be the tool you need to bridge the gap. Now we're diving into a fundamental concept in machine learning, the bias-variance trade-off, and how regularization plays a critical role in managing it. This trade-off is the balancing act between two competing forces in model performance, bias and variance. If you've ever wondered why your model struggles to generalize or feels unstable, it's probably because this trade-off isn't being managed properly. Let's start by understanding the two sides of this trade-off. Bias. This occurs when a model is too simple to capture the underlying patterns in the data. Think of it as an overly rigid, narrow approach. High bias leads to underfitting, where the model performs poorly on both training and validation data. Variance. This happens when a model is too complex, fitting even the noise in the training data. High variance leads to overfitting, where the model performs well on training data but fails to generalize to new, unseen data. The goal of machine learning is to find the sweet spot between bias and variance, where the model is complex enough to learn meaningful patterns, but not so complex that it memorizes noise. His is where regularization becomes a game changer. By applying techniques like L1 regularization, Lasso, or L2 regularization, Ridge, you can control the complexity of the model. These techniques add a penalty term to the loss function, which discourages overly large parameter values. When variance is high, overfitting, regularization reduces model complexity by shrinking coefficients, ensuring the model doesn't rely too heavily on specific features. When bias is high, underfitting, regularization can also help by stabilizing learning and encouraging the model to capture broader patterns, especially when combined with cross-validation to avoid excessive regularization. The result? A well-regularized model that achieves the right balance between bias and variance, improving its ability to generalize to unseen data. Let's make this concrete with an example. Imagine you have a dataset of 1,000 samples and you're training a regression model. Without regularization, the model achieves 95% accuracy on training data, but only 70% on validation data, a clear case of overfitting due to high variance. With L2 regularization, training accuracy might drop slightly to 90%, but validation accuracy improves to 80%, indicating better generalization. This shows how regularization helps shift the model from overfitting toward the ideal balance point. In practical terms, managing this trade-off is critical in real-world AI systems. Healthcare AI. A diagnosis model that overfits to one hospital's data may perform poorly when deployed at another hospital. Regularization ensures the model captures general medical patterns rather than site-specific details. Finance. In credit scoring, a highly complex model might overfit to past financial trends, making it unreliable for future predictions. Regularization balances complexity, creating models that perform consistently across time. Autonomous vehicles. Self-driving car models must generalize to different weather conditions, terrains, and lighting scenarios. Regularization ensures they don't overfit to specific training environments. The bias-variance trade-off isn't a problem you can solve once and forget. It's an ongoing balancing act. And regularization is your most powerful tool for managing it. By applying the right amount of regularization, you ensure that your model captures the meaningful patterns in your data without getting lost in the noise. It's not just about improving performance, it's about building models that are robust, reliable, and ready for the real world. And now that we've seen how regularization balances bias and variance, the next big question is, what are the common pitfalls to avoid when using regularization? Because while regularization is a powerful tool, it's not foolproof, and making the wrong choices can hurt your model more than help it. That's exactly what we'll explore next. Now let's talk about something that doesn't get enough attention, the common mistakes and pitfalls in using regularization. Because while regularization is a powerful tool for preventing overfitting and improving generalization, it's not a magic fix. If it's applied incorrectly or without careful consideration, it can actually make your model worse. So let's break down 3 common pitfalls that people run into when applying regularization, and more importantly, how to avoid them. Let's start with one of the most common issues, over-regularization. When you apply too much regularization, your model can become too simple, losing the ability to capture important patterns in the data. This leads to underfitting, where the model performs poorly on both training and validation data because it's been stripped of its complexity. Think of it like trying to build a house with too few materials. Sure, you've reduced costs and complexity, but the result is a house that isn't functional. In the same way, over-regularizing a model makes it too simplistic to solve the problem at hand. How to avoid this? Use cross-validation to find the optimal level of regularization. Instead of guessing the penalty term or dropout rate, test different levels systematically to ensure you're not restricting the model too much. Here's a lesser-known but critical pitfall: ignoring feature scaling when using regularization techniques like Lasso, L1, or Ridge, L2. Regularization penalizes coefficients based on their magnitude, but if your features are on vastly different scales, say one feature ranges from 0 to 1, while another ranges from 1,000 to 10,000, the penalty will disproportionately affect features with larger values, regardless of their importance. This can lead to biased results, where the model underestimates the importance of certain features simply because they're on a different scale. How to avoid this? Always standardize or normalize your features before applying regularization. This ensures that all features are treated equally during the regularization process, allowing the model to make unbiased decisions about which features to prioritize. Another major mistake is relying solely on training accuracy to evaluate the effectiveness of regularization. Regularization is designed to improve generalization, so its true impact can only be assessed by looking at validation or cross-validated performance metrics. If you're only checking training accuracy, you might assume that regularization isn't working, when in reality, it's improving the model's ability to handle unseen data. And again, how to avoid this? Always evaluate your model on a separate validation set or through cross-validation. Use metrics like validation accuracy, F1 score, or mean squared error to determine whether regularization is actually improving generalization rather than just focusing on training performance. Regularization is one of the most important tools in machine learning, but it needs to be applied thoughtfully. By avoiding these common pitfalls, over-regularization, ignoring feature scaling, and inadequate evaluation, you can ensure that your regularization techniques are actually helping your model rather than holding it back. And now that we've covered what not to do, the next big question is, what are the most advanced regularization techniques and how can we use them to take our models to the next level? Now it's time to level up. We've already covered the fundamentals of regularization, things like L1, L2, and dropout. But as machine learning models get bigger, more complex, and more versatile, we need more advanced tools to keep everything under control. So in this slide, we're diving into some of the most powerful and cutting-edge regularization techniques and how they can help you build better, more reliable AI systems. Let's start with dropout, one of the most widely used techniques in deep learning. Dropout is all about adding controlled chaos during training. At each training step, it randomly disables a fraction of the neurons in the network. Why? Because neural networks often become over-reliant on specific neurons or pathways, which can lead to overfitting. By randomly dropping out neurons, the network is forced to learn redundant representations, patterns that are distributed across the network rather than concentrated in just a few neurons. Here is how it helps. Dropout improves generalization by making the model more robust to noise and variability in the data. It's commonly used in deep learning models, with dropout rates typically ranging from 20% to 50%. Sometimes the best way to regularize a model is to simply stop training at the right moment. That's what early stopping does. As you train a model, it becomes increasingly good at minimizing the training loss, but at some point it starts overfitting to the training data and the validation loss begins to rise. Early stopping allows you to monitor the model's performance on a validation set and halt training as soon as it starts to degrade. How it helps. By stopping at the optimal point, early stopping ensures that your model doesn't waste time learning noise or irrelevant patterns. It's particularly useful when training neural networks, where overfitting can happen very quickly. Here's a simple but incredibly effective technique: data augmentation. Instead of just regularizing the model, you can also improve generalization by increasing the diversity of the training data. How it works. Data augmentation involves creating modified versions of your training data. For example, in image classification, you can rotate, scale, flip, or adjust the colors of images. In text processing, you can paraphrase sentences or replace words with synonyms. And again, how it helps. By exposing the model to a wider variety of data, data augmentation makes it more robust to variations in the real world. It's particularly effective in image classification and NLP tasks where data diversity is critical. Of course, no discussion of regularization would be complete without mentioning the classic techniques: L1, Lasso, and L2, Ridge. L1 regularization encourages sparsity by shrinking some coefficients to exactly zero, effectively performing feature selection. L2 regularization stabilizes the model by penalizing large coefficients, ensuring that no single feature dominates the predictions. Why they help? Both techniques are highly effective for reducing model complexity and preventing overfitting, especially in high-dimensional datasets. Finally, let's talk about batch normalization, a technique that has become a standard in deep learning. Batch normalization works by normalizing the inputs of each layer during training, ensuring that the network learns at a stable pace. It reduces something called internal covariate shift, where the distribution of inputs to a layer changes as the network trains. How it helps: by stabilizing the learning process, batch normalization allows you to use higher learning rates, reduces sensitivity to weight initialization, and even acts as a regularizer, making your model less likely to overfit. These advanced regularization techniques, dropout, early stopping, data augmentation, batch normalization, and the classics like L1 and L2, are designed to tackle the unique challenges of modern machine learning. They're not just about improving generalization, they're about building models that are robust, scalable, and ready for real-world deployment. And now that we've explored these cutting-edge tools, the next question is, how do we apply them in specific real-world scenarios? Let's shift our focus to real-world applications and see how regularization plays a crucial role in making machine learning models not only effective but also reliable across industries like healthcare, finance, and natural language processing, NLP. Because here's the truth: regularization isn't just a technical detail, it's the key to building models that work under real-world conditions, where data is messy, inconsistent, and constantly changing. Let's start with healthcare. Imagine you're developing a model to predict patient readmissions, a critical task for optimizing hospital resources. Without regularization, the model might overfit to specific patient demographics or hospital-specific data quirks, making it useless when applied to other hospitals or regions. By using L1 and L2 regularization, you can ensure the model focuses on relevant medical features like age, comorbidities, and lab results rather than noise in the data. This reduces overfitting, allowing the model to generalize better to new patient populations. Case study. In a study on patient readmission prediction, applying regularization improved prediction accuracy by 15%, helping hospitals allocate resources more effectively. Next, let's talk about finance. Whether it's credit scoring, fraud detection, or risk modeling, regularization is critical for managing the complexity of these models. Take credit scoring systems, for example. A poorly regularized model might overfit to historical data, flagging certain customers as high risk simply because of outdated correlations that no longer apply. By using techniques like elastic net regularization, you can balance feature selection with coefficient stability, reducing the impact of noisy or irrelevant financial indicators. Build a model that generalizes better to changing economic conditions and evolving customer behavior. Real-world impact: elastic net regularization has been shown to reduce false positives in credit scoring by 20%, allowing financial institutions to make more accurate lending decisions. In NLP, regularization is indispensable for building robust models that can handle the nuances of human language. Without proper regularization, models like sentiment analyzers or text generators can overfit to specific phrases or styles in the training data, failing to adapt to new text. Key regularization techniques in NLP. Dropout ensures that transformer-based models like GPT or BERT don't over-rely on specific attention heads. L2 regularization stabilizes weight updates, improving model performance on unseen data. Real-world example: regularization has been shown to improve perplexity scores, a measure of prediction quality, by 15 to 30%, enabling models to generate more accurate and contextually relevant text. Across industries, regularization ensures that machine learning models aren't just accurate, they're reliable, fair, and scalable. In healthcare, It prevents models from overfitting to specific patient populations, improving outcomes across diverse demographics. In finance, it ensures that risk assessments are based on generalizable patterns, not outdated correlations. In NLP, it makes language models adaptable to new text styles and use cases. And now that we've seen how regularization applies to these industries, the next step is to summarize everything we've learned about regularization techniques and their role in machine learning. Let's bring it all together. We've covered a lot of ground on regularization, from understanding its fundamentals to exploring advanced techniques and real-world applications. Now, let's bring it all together and recap the key regularization techniques that empower machine learning models to be accurate, robust, and generalizable. Because at its core, regularization isn't just a tool, it's a mindset for building better models that thrive in the real world. At its heart, regularization is all about preventing overfitting. It ensures that models don't just memorize training data, but instead learn generalizable patterns that can handle new, unseen data. Whether it's a simple linear regression or a massive deep learning model, regularization is the key to achieving balanced, reliable predictions. Let's break down the major techniques we have explored. L1 regularization, Lasso L1 regularization adds a penalty equal to the absolute value of the magnitude of coefficients. Key benefit: promotes sparsity by shrinking some coefficients to exactly zero, effectively performing feature selection. Best use case: high-dimensional datasets where irrelevant features need to be removed. 2. L2 regularization, L2 regularization adds a penalty equal to the square of the magnitude of coefficients. Key benefit: stabilizes the model by penalizing large coefficients, preventing over-reliance on specific features. Best use case: models prone to multicollinearity or when you want to reduce overfitting while keeping all features. 3. Elastic net regularization. Elastic net combines both L1 and L2 penalties, balancing feature selection with coefficient stability. Key benefit: handles correlated features better than L1 or L2 alone. Best use case: datasets with many features, especially when some are highly correlated. 4. Dropout in neural networks. Dropout is a technique where a random subset of neurons is dropped out, set to zero, during training. Key benefit: prevents over-reliance on specific neurons, forcing the network to learn distributed, robust representations. Best use case: deep learning models, particularly in image recognition and NLP tasks. At this point, you might be asking, which regularization technique should I use? The answer depends on your model and data. If you're working with a linear model and have many irrelevant features, L1 regularization can simplify the model. If you want to stabilize a deep learning model, dropout and L2 regularization are great choices. For ensemble methods, techniques like feature subsampling and early stopping keep models efficient and generalizable. Regularization isn't just a technical adjustment, it's a foundation for building scalable, trustworthy, and high-performing AI systems. It ensures that models are robust under real-world conditions, able to handle messy data, changing trends, and unpredictable challenges. Whether you're working on healthcare, finance, NLP, or autonomous systems, regularization is what transforms a model from good to great. And as machine learning continues to evolve, so will regularization techniques. The question now is, how will you use these tools to build the AI systems of the future? Feel free to answer this question. There are some little space in the comment section left.